recording. Oh, yay. Okay, it's recording. Excellent. So I wanted to go over one of the questions from the Poggle, because it was the one that everybody asked me about. Why is it not turning on? Oh, because it needs to warm up. Okay, that's all right. So it was question number 19, probably, yeah. So that would be on page 56, I think. Why are none of my pens working? That's sad. Huh. Oh. Okay, this one will work. There we go. All right. Back up, back up, back up. Do I not have page 19? What the hell? Oh, no. Oh, that's because I'm on the wrong page. That's because I'm on the wrong page, 49. Except for we want 56, that's right. So the question number 19 is which wavelength in figure 8 would allow you to measure the lowest concentration of compound X and explain why this wavelength was chosen. So what we have is we have here, yes? Oh, it's not, oh, it got unplugged, that's great. Oh, that's right, because I was gonna take it to Mr., because I couldn't log in this morning. Okay, there we go. I am recording, thank you. Thank you for checking. This particular graph, we're changing the wavelength, that is our independent variable, okay? That means all our other variables other than absorbance, which is the dependent variable, all the other variables have to be held constant, okay? So they are controlled variables. So we are holding concentration constant, and we are holding the path length. And the path length just depends upon this little thing. It looks a bit like a test tube sometimes. Sometimes it looks like a little square. I can't draw a square, but anyway, it's called a cuvette, but it, honest to God, sometimes just looks like a test tube. They're just made a little more carefully so they don't have like imperfections, so they won't absorb light. You want it to be a really high quality glass, whereas a test tube, you don't really care about the quality, right? You don't care if the light can pass through a test tube, but these cuvettes, you do care. And almost all cuvettes are 1 centimeter across. So your path length, which is L, is going to be 1 centimeter. So that's held constant. You're going to have a solution in here, and its concentration will be the same. And the only thing that you're going to be changing is the wavelength. Yes? Let's say that this was 0.1 molar. If I now did another, we call this an absorbance spectrum. If I did another absorbance spectrum for the same substance, but now I did it at 0.05 molar, what would you expect it to look like? Have a chat with your neighbor. What would you expect it to look like if we now did one at a lower concentration? What do you guys think? Yeah, it's going to be lower. By how much? Half as much. Yeah, it's going to be by a factor of 2. So you would have your point maybe here and then here and 1, 2, 3, 2, 3, 4, 5, 2.5 there. 1, 2, 3, 4, 5, 6, 7. So that's going to be about 3.5. You know, so you're going to have something that looks kind of like this. Yeah? Now, as the concentration gets lower and lower, what if we did our measurements at 200 nanometers? What if we had now 0.02 molar? What would happen to the absorbance at 200 nanometers? Yeah. And we're getting into the range where it becomes unmeasurable, yes? So what we want to do is we want to choose, and we'll use this for the rest of the experiment. So what you do is you actually do 2 graphs. You do 1 graph at a fairly decent concentration, and you get this profile, and you say, I'm going to select this wavelength here. We actually call this wavelength lambda maximum. And you can write it as lambda. Do you guys know how to write a lambda? You're good with that? Okay, lambda max. And that is the wavelength you want to choose when you do any of your other experiments with it. So for example, there is a lab where you can take some crystal violet, which is a dye, and you put some bleach in it. And then you pop it into the spectrophotometer, and you take readings every minute or so. And what happens is that the dye will, with the bleach will react with the dye, and it will start to get lighter and lighter and lighter. And so the absorbance will get less and less and less. And if this were crystal violet, we would choose to do that one where we're measuring the absorbance every few minutes. We would choose to do that at a wavelength of about 233 nanometers, because that would give us the best absorbance. We wouldn't like sort of bottom out somewhere where we couldn't do that. Is good? Were there other questions from either the POGL or from 1.1a? Yes. Oh, the absorptivity constant. It's just a constant, and you actually calculate it. Let's see, do I have that one here? You know what? Let's watch this little video because it's not that long. Okay, it's 8 minutes, and it will show you where you're going to go next with it, okay? So this is on page 68, page 68. 68.
Hello everyone, this video is to give you a quick overview of the Beer-Lambert law and how we use it in chemistry. Unlike the name suggests, the Beer-Lambert law has absolutely nothing to do with beer. It's actually named for these two guys, Beer and Lambert, who were the first to recognize that the absorbance of light is a law and how we use it in chemistry lab. Unlike the name suggests, the Beer-Lambert law has absolutely nothing to do with beer. It's actually named for these two guys.
Speakers. Play. Beer. It's Beer's law.
Hello everyone, this video is to give you a quick overview of the Beer-Lambert law and how we use it in the chemistry lab. Unlike the name suggests, the Beer-Lambert law has absolutely nothing to do with beer. It's actually named for these two guys, Beer and Lambert, who were the first to recognize that the absorbance of light is related to the concentration of whatever they were looking at. This is a very powerful technique for the analysis of samples in the chem lab, and it's something we'll be using fairly frequently during the semester.
No, we won't.
Whenever you're in lab, it's not uncommon to run into solutions that we know the concentration of. In this example, here are 5 cobalt solutions that vary in concentration from 0.1 molarity to 0.5 molarity. The reason we chose cobalt for this example is cobalt is red in solution. So hopefully you can see that as my concentration increases from left to right, the depth of the red color also increases correspondingly. So low concentration, not much red color; high concentration, a deep red. It is not uncommon to run into solutions in lab that I don't know the concentration of. So for example, here on the right is a solution of that same cobalt that I don't know its molarity.
If you had to guess, what would you pick for the concentration of that unknown? 0.3, 0.25, somewhere in there, yes? And you could guess like that. Is that a particularly, precise technique? No. So we're going to get better at that by running next what we call a calibration curve. It actually is not a curve, it is a straight line, but we call things curves when it's a scatter plot and you draw it, it's just called a curve, even if it's a straight line.
I can estimate the concentration of that unknown based on the color of red in that solution. And if I look carefully, I can see that red color over here on the right is darker than the 0.3, but it's definitely lighter than the 0.4. So that molarity is going to fall in between those two solutions. Maybe I would estimate 0.35. Sometimes an estimate is good enough. However, there are many times we need some more accuracy. And to get that accuracy, we're going to use an instrument called a spectrophotometer. A spectrophotometer is an instrument that can pass light through solutions. When we do this, we know how much light is being sent in to the solution, and we measure how much comes out. And there's always going to be a difference in those two readings. In this figure, you can see I'm passing quite a bit of red light into the solution. Some of that light is getting absorbed by the solution. So when it gets done traveling through it, less light comes out. What Beer-Lambert did was they put some mathematics to this relationship. And the Beer-Lambert law is given by this equation. The absorbance at a given wavelength or color of light, which I'll get into in a second, is related to 3 terms. A constant E, which is a constant for whatever chemical we're looking at, the path length, and the concentration. The path length and concentration are important because the path length is the amount of distance the light passes through the solution. So the path length in our example is very short, it's just the width of the container. But these can be very narrow or very wide, so that's going to change some things.
Now, yes, the path length can change, but I'm almost guaranteeing you for anything you do in like your undergraduate, you're going to be using a 1 centimeter cuvette. Like I think the chances of you having anything else is very, very rare.
And the concentration, which here I show in molarity because chemists work in molarity very commonly, but the truth is, Beer-Lambert law works for any concentration unit as long as you're consistent. Thankfully, we don't need to work with this Beer-Lambert law in this form. We usually look at it in a slightly different way. The way that chemists work with Beer-Lambert law is we go back to those 5 solutions that I know the concentration of. So here you can see I've got my 0.1 to 0.5 molarity solutions. I'm going to put those into my spectrometer, and I'm actually going to measure the absorbance.
So unlike when we were doing the absorbance spectrum, that one had only one concentration, and we changed the wavelength every time. This time, what are we doing with wavelength? It's constant. So every time we're keeping the wavelength constant. What are we changing this time? The concentration. So we're going to see that now the dependence of, and how did they choose? How did they choose that 472 nanometers? What would they have done? They would have done that highest peak, okay, in the absorbance spectrum.
If you look now, I've got this extra term in here that says absorbance at 472 nanometers. This 472 nanometers lets whoever looks at my data know what wavelength of light I'm passing through the solution. The way to think about this is actually color. 472 nanometers falls in the visible range, and it's actually some green light. So I'm passing green light through these red solutions. What I hope you notice is that as my concentration increases, my absorbance also increases.
Why did they choose green light to go through the red solution? Yeah, green and red are opposite one another. So if it looks red, it's because red light is passing through and the green light is being absorbed. Yes? 472? They would have run earlier on, that they don't show here, they would have done a spectrum like the one we saw earlier today, and they would have picked the highest peak, and whatever that wavelength is, that would be the 472. Okay, so with any concentration, it will be the highest peak. Do you remember when we, I don't want to go back to it now because the video will have like a hissy fit, but do you remember how we had the one that was a little taller and the one that was shorter? So it doesn't depend on the concentration where that highest part of the peak is going to be. Yeah, so we choose that one. Yeah, perfect.
So as I get more stuff in there, more of that light's being.
Sorry, yes. 472 should be green. Yeah. Yeah. And we can check that out later if you want to. Just be sure.
Once I have this data, I use it to create a Beer's law plot. A Beer's law plot is just absorbance plotted against concentration. So I've got absorbance on my y-axis, concentration on my x. Once I plot my points, it's very common to fit a trend line. So here's the equation for that trend line, and an R-squared value to that number.
Okay, now, do you guys know how to plot a graph in Excel? If you don't, there is, you can do it on your own. On page 72, there's a few little how to graph by hand and how to graph by Excel. I'm not going to spend any class time on it because chances are on the AP exam you will never have to do it. And if it's not on the exam, we're going to spend very little time on it. Okay, but if you ever need to, there's a couple of references in there for how to graph by hand or how to graph in Excel. But Excel will do the linear regression for you. Yes? And it will spit out your best fit line with your y equals mx plus b. Okay? What is m? What does m stand for? The slope. Yes? So you could calculate the slope by picking 2 points on your line. How do you calculate a slope? Rise over run, delta y over delta x, yes? Okay, but Excel will do it for you. What would the units, now absorbance, this is absorbance at 472 nanometers. What is the unit of absorbance? It doesn't have a unit, okay? So what is the unit of the slope? What is the unit of the slope? absorbance over concentration. And if we plug units in there, what's the unit for absorbance? Nothing. Okay, so we'll put a 1. I know it says nanometers there. That's not because it's measured in nanometers. It's because this is the absorbance at 472 nanometers. Okay, sometimes they won't even put that there. It'll just be at the top. Okay, the 472 bit, because it can be a little confusing. So we don't have a unit here. What's the unit of concentration? Moles per liter or molar. Okay, so you could write it like this. How else could you write that unit? You could write it as liters per mole. How did we get there? We took 1 over moles per liter, so that's reciprocal of moles per liter, and so we get liters per mole. There are other ways you could write this as well. I'm going to introduce them to you because in the kinetics part of it, we will see molarity upside down like that. Can you do it with a negative exponent on one of these things? Yeah, you could say this is liters times mole to the -1. Yeah? Or if you wanted to, you could take this one. What could you rewrite this as with an exponent? You could write it as molar to the -1. So just get familiar with, like, start being okay with flipping things over and putting negative exponents on them, because you will see those units coming up in rate law stuff later. Yes? In the spectrophotometer. So they put it in and it actually comes out. You guys are going to go home tonight and you're going to do a little experiment on the computer where you actually practice doing it. Yeah, it comes from out from the instrument. It actually gives you a little display and you just read the display. Yeah. Okay. So let's just carry on with this. Whoops, there we go. Is it playing? No, it's not. Play.
Once I have this plot, I can use it to figure out the concentration of my unknown. The way I do that is I take that same unknown solution, I put it in a spectrometer, and I measure its absorbance at exactly the same wavelength, 472 nanometers or that green light. When I did this for this example, it comes out to 0.47.
So that's our unknown now.
If we look back at the original data for our 5 known molarity solutions, it falls between the 0.3 molarity and 0.4 molarity solutions, which should make sense. That's where we estimated it way back when we were just looking at color.
And right now we're still estimating it. We're just comparing the absorbance of the unknown with the absorbance of the concentrations that we knew already. Yes? So it's somewhere in between there. But again, we're still approximating. So let's get better yet.
So that's a good thing. We can also look at it here on the plot. We can find the absorbance on the y-axis, since that's where it lives. So 0.47 is about where that black arrow is. We can draw a horizontal line to where it intersects with that trend line, and we can drop it down to the x-axis, which is my concentration. And eyeballing that, we got a molarity of about 0.35.
Okay, so that's maybe 0.35, maybe 0.34. Like, it's hard to exactly tell, but, you know, that's what you're doing. That is a perfectly, if they give you and this is something that could show up on the AP exam, is they could give you a graph like this, say this was the calibration curve. That's what this is called. This one is called a calibration curve. And it's done with known concentrations at usually lambda max, unless there's a really good reason not to. Sometimes you'll have 2 substances, but we're not going to be that fancy this year. Okay, like sometimes you'll have 2 substances and they'll both absorb and you'll want to get one, and so you'll pick a different area. Anyway, so this is a calibration curve. We do it with our known substances, and we can just read directly off the graph to get our concentration of our unknown. Is good? Cool. Is good? No? Yeah? Okay.
Again, that's as good as our eyeball with just the colors. We can.
Can you think of a way that you could be more precise? Math. What would you do to figure it out? You would what, sorry? Yeah, you would use the slope. So you would just plug in your y value, 0.47, right? And you would solve for x. Is good? Yes?
We can do even better with a little bit of mathematics. The mathematics comes from this trend line equation. If we look at that equation from the plot, again, I just pulled it off of there, we need to recognize what each of the variables are. In this case, y is my absorbance value, and x is my concentration value in terms of molarity. For our unknown solution, we know the absorbance. So to figure out concentration, all I need to do is plug that in for my y and solve for my x. So here on the right, I do show the mathematics. I set it equal to 0.47, and I isolate for my x term. So move everything around, get the x by itself. I get a 0.34 molarity solution, which is really close to my estimate. But this is a much more accurate way to get that concentration.
So on the AP exam, if they give you the equation, you can use the equation. If they do not give you the equation, you can read it off. If they give you both, you can choose. Yes? There really shouldn't be, because really the absorbance should be 0 if there's 0 concentration. It may just be that there's some like imperfection in the cuvette or something like that, although you're supposed to kind of deal with that when you run it, and you'll have practice doing this when you do the little experiments tonight. You're supposed to put in a blank cuvette first that just contains your solvent, so that it takes into account any background absorbance by the solvent or the cuvette itself. So it should be 1 sometimes, because life is not perfect, or sorry, it should be 0, the y-intercept, but sometimes because life isn't perfect, it just isn't. And we just live with it. Yeah.
Beer's law is pretty easy to work with, but there is one major consideration that we always need to pay attention to when we're using it. When working with Beer's law, again, we're going to have some standards. Again, those are known molarity solutions, and we can measure concentrations of unknowns. So in this example, I've measured an unknown there. I could drop it down, figure out its concentration, or if I had the trend line equation, I could do the math. The problem arises when I get unknowns that have absorbances that don't fall between the standards. So that one's going to fall way up there. We'd like to think that if we did the mathematics, it would still give us good data. But the truth is, Beer's law is only linear or straight line for short distances, and we can only trust it between our standard points. The take-home message from this, if you're measuring the absorbance of an unknown, it must fall in between the standards. So in this case, where my mouse is indicating between standard 1 and standard 4, that's where all of our unknowns have to fall. If they're outside of that range, we need to do some adjustments. If it doesn't fall in the range of our standards, one fix is to add more points to the line. Make a more concentrated or more dilute standard just to get it on the line. The other way to do it, and is more common, is you take and you dilute your unknown sample. So maybe unknown 2 is way too concentrated. I can cut it 50-50 with water. That may pull it down somewhere in between my standard points, which will give me a good result.
Yes? No, no. So it should be between them all. Is AP going to ask you any of this? I don't think so. Like, honestly, I think it's going to be like, pick the right wavelength, and they'll give you an absorbance, and you need to say, it's that one up there. And it will say, what's the concentration of your unknown? Its absorbance is, 3.2. Oh, it's that concentration there. Honest to God, I think that's all you're going to have to do with it. However, if you don't have an understanding of it, then it becomes confusing, right? You're like, why am I picking that top one and things like that. So yes, if you go on to university, it might be nice to know that Beer's law, it does tend to do this once you get to sort of higher concentrations, and so you could not estimate a point on the straight line because it will be inaccurate. Yes, but if you're not doing a chem lab, so you might come back to this, you know, when you're in university and be like, oh yeah, Beer's law, it doesn't necessarily go straight. All right, we're going to go to then page 73, I think, because that's basically it. Okay, so here is our calibration curve. And you can use it to do several things. You can, or a couple of things. You can use it like we did before, where you say, I have an unknown with an absorbance of 0.8, and you can read down and say that's going to be a concentration of about 0.42 molar. You can also use it to find the molar absorptivity constant, which is where we were going all along with this, because I forget who it was who asked about it, but we wanted to know about the molar absorptivity constant. How do we get that number? We get it from the slope of the calibration curve. Okay? And we don't have to do anything fancy with it because our path length, so y is the slope E, because we know that y is absorbance, yes. X is concentration, yes. As we were talking about before, the y-intercept, technically, if you have no concentration, you should have no absorbance, so there's no y-intercept. And most cuvettes have an interior width of 1 centimeter. And usually the units of the molar absorptivity constant are given like including a centimeter term. So it just kind of goes away because it's just 1. Okay, again, do you need to be able to do this for the AP exam? No. But it just shows that if you make the assumption that your path length is 1, okay, then it just leaves us with A is equal to EEC. All right, and we've got our y equals mx plus b. Y is just equal to mx because we don't have a b. And you can see that A, absorbance is on the y-axis, concentration is on the x-axis. What is our slope? It's the absorptivity. So what would the unit of absorptivity be? The molar absorptivity constant, that letter epsilon, I think that, is that an epsilon? I think it is. Yeah. Oh, but there isn't, to be honest, there actually is centimeters in there as well. So if we look at absorbance equals the molar absorptivity times C times L. So let's just solve for the molar absorptivity. Do that algebra yourself. Go, do it. Just making sure. I had a student who got a 5 on the AP exam, and he lost marks on his gas test. We had time to do a gas test back then in the olden days. He lost marks on his gas test because he could not solve the ideal gas equation, not do the algebra on it. I'm like, ah, you're so smart. Why did you not do the algebra? Anyway, so we have A over C L. What's the unit of absorbance? Nothing. Okay, yes, absorbance. Concentration? Molarity, moles per liter. And what's the unit of path length? Centimeters. So let's make that a little tidier. Let's just put everything up top. So we have L per mole centimeter, or liters, mole -1, centimeter -1, or molar -1, centimeter -1. Huh? Meters in a liter? No. Oh, well, a cubic meter is 1,000 liters. I don't know if that's what you're asking. I feel like it's not. Okay. So how are we feeling about that? Pretty good? Excellent. So let's see what I wanted to let's just finish up with this other video that we had from last day, because we got most of the way through it. We might as well finish it today. So this is on page 57, 58 probably at this point.
So in this lecture, in another lecture, okay? So we're color, then the color opposite is being absorbed.
Okay, we saw here yesterday. Yeah, this is where we got to. Good, good, good.
This is just a picture of one of the spectrophotometers we have in our room. It's an older model. It's a kind of basic model made by Flynn. The ones you'll be using are slightly different, but they all have essentially the same parts. They have a little place where you can insert the sample. Then they have a number of ways that you can adjust the wavelength of light, and then a place where you can read the absorbance and percent transmittance.
So if you're like, where am I seeing the absorbance? It's going to be on the little digital display here. Okay, and you're going to be putting your sample, this opens up and you pop your sample into it. You set your wavelength here, and there's some zero control knobs down here in order to calibrate your spectrophotometer. Make sure you've zeroed it for the blank with the solution, or sorry, the solvent and the cuvette and nothing else.
Okay, so what's going on inside this little box? How does this all work? Take a look at this diagram. This is basically what's going on. So we have a light source. Okay, and the light source is typically white light, contains all wavelengths. The first thing we want to do is we want to collimate the light, or essentially make all of the wavelengths parallel to one another. So there's a special collimator or a lens that does that. Then we pass that light beam through a prism, okay, or a diffraction grating. And what that does is that splits the light into its various wavelengths. So for regular white light, you get all the colors of the rainbow. Now, the spectrophotometer doesn't just shine all of that light at your sample. It actually shines a very specific wavelength of light. And you can choose that. You choose that by, normally by moving a slit in the way of the one wavelength of light or color that you'd like to shine through the sample.
Okay, so some of the time, some spectrophotometers will have a prism and they'll move the slit up and down to get the correct wavelength of light. Other ones, instead of having this, there's like a diffraction gradient. Are you familiar with those at all? Do you know what they are? Have you seen a CD? Have you seen how it makes like rainbowy stuff? That's because it's got all kinds of little lines on it, yes? And it makes a rainbow, it splits the light. And so instead of having a prism, you can have something along the lines of a CD, and it splits the light just like a prism would. And you can actually take this thing and you can tilt it, and depending on which way you tilt it, one of the light colors will go through the slit. Do you need to know how a spectrophotometer works in order to do the AP exam? No.
Okay. That particular color of light will then shine through the sample. Some of it will be absorbed. Some of it will be transmitted. IO is the incident light that first enters, and IT is the amount of light that's transmitted through after some has been absorbed. The remaining light that gets through hits a photocell. A photocell is a solid-state detector that picks up how much light, and then it prints out on a digital display either absorbance, how much was taken away, or percent transmittance, how much light actually got through.
So your device will actually you will be able to either select transmittance and it'll report the transmittance, or you push another button and you go like, I would like it to say absorbance, and it'll give you absorbance. Okay? There we are. I think that's about all we wanted for that. I don't think there's anything else in here, is there? No, not really. He just goes on and on about it. Blah, blah, blah. Ideal wavelength. Greatest absorbance. Yeah, we've done all that. Okay, cool. I'm going to leave spectrophotometry for today. Like I said, you're going to go home and do some stuff on it. Okay. We all did okay on 1.1. So let's go to our other book. We need to charge through the regular material as well. Okay. How are we feeling about ionic reactions? Let's think about it for a minute, and then once you've thought about it for a minute, we're going to do thumbs up, thumbs in the middle, or thumbs down on ionic reactions. Ionic reactions. Are we feeling thumbs up, thumbs down, thumbs in the middle? Okay, I got enough people saying in the middle or down that we're going to go through this really quickly. If you're like, I don't need to go through this and you would like to get started on today's homework, you could put in earbuds and start using a little spectrophotometer or something. You could actually, the rest of 1.7b, you could watch the video for that, okay? Or you can hang out with us and just review ionic reactions. All right, there are two types of ionic reactions. Do you remember what they're called? Complete and net, yes. So we have the complete and the net. The CIE, let me know if that flickers out again. Something's a little weird. And the NIE. We can do these we can do them for double replacement. See if you can remind yourself in your head what a double replacement looks like. We can do it for a single replacement. We can do it for neutralization. Usually not for synthesis and decomposition because we're not usually working with solutions. And when you don't have solutions, you usually don't have ions floating around. Okay, so like if I gave you a piece of magnesium and I went and I burnt it, it would combine with the oxygen, but there wouldn't be ions floating around. When we're doing an ionic equation, it's when we have ions floating around in solution. Okay, so these are used for ions in solution. So let's try a double replacement reaction. And in fact, you guys could pull out your pink data sheet. And so there's pink and there's salmon, okay? And then there's yellow and green. So we're looking for the pink one, and we're going to go to page, I think it's 4. Page 4. Does this look familiar? And if it doesn't look familiar, if you're like, I did not have Ms. Spence's page 4 last year and we did not do this in Chem 11, that's okay. We're gonna review it right now. What does it mean if I have all negative ions and they are with positive ions, alkali ions, they're soluble? What does soluble mean? It means they are exactly, a significant quantity will dissolve in water. Now, in this particular case, I would like you to tell me how much is considered a significant quantity. Look at your sheet. Yes. More than 0.1 moles per liter. Yes. More than 0.1 moles per liter is considered a significant quantity. You will not have this chart for the AP exam. You will have it for your in-class exam. You don't need to know anything for AP because they will tell you other than a very few rules that you should memorize. There's not very many. Do you guys remember the ones that you should memorize? Alkalis. So these are going to be our always soluble. Hydrogen, I'm going to leave hydrogen alone because hydrogen is an acid, it works as an acid, and acids do their own thing. But yes, alkali metals are certainly one. This is just, I'm just writing stuff, okay? This is not on a page. Ammonium. Nitrates. And as long as you know that those ones are always soluble, everything else will be given to you in the question, okay? But they will expect you to know these ones. So if they're like a precipitate forms and your two products, if one of them contains an alkali ion, that will not be the precipitate. If they tell you a precipitate forms, then it must be the other one, yes? So let's say, for example, we had, oh, let's just do our favorite, PB, NO3, 2. And if I put that in water, will it be solid or will it be aqueous? It'll be aqueous. Why? Because always soluble. So it is aqueous. We can have Ki, which if we put that in water, it will be aqueous. Why? Because it has iodine? Because it has potassium, and potassium is an alkali. Where are your alkalis on your periodic table? Column number. Okay. Now let's predict our products for this. Do you remember how to predict the products for a double replacement reaction? You swap the ions. One of the easiest ways to do it is to write out all the ions with their charges. So you can say, okay, I know that I have PB, I know I have NO3, I don't care that I have two of them. I know I have potassium and I know I have iodine. And when I write out my ions, what else do I need to include? Charges. So we're going to start with K and I. What are the charges on K and I? 1 and 1, because all your alkalis are +1 and all of the halogens are -1, okay? And you should know those, and if you weren't in my class last year, or you didn't learn it, or you've forgotten it, come and see me and I can give you a quick update on it. Okay, now, what is the charge of nitrate? -1. Okay, you should know nitrate is one of the most common ions, so know the charge of nitrate. Okay, in that case, what is the charge of lead here? +2. To predict the products of a double replacement, we're going to combine the outside ions. So we're going to take the ions that are on the outside and we will combine them. So we're going to take lead and put it with iodide. Yes? You would need to be able to figure that out from the fact that you have a compound and a compound, and they're both ionic compounds. So double replacement, 2 ionic compounds. Good? Okay. So we have lead, we have iodide. What would we get? Pb, I2. Excellent. Okay. And our other product would be, now we're going to combine the inside ions. And I hope you guys know which one goes first, but just in case, I always go forwards on the outside ones and then go backwards on the inside ones, and that's always going to put your cation first, okay? I don't want to see any NO3K. All right, I don't think many of you would do that, but sometimes our brain has fallen asleep over the summer, and you know what I mean, right? It could happen to the best of us. So we go forwards for the outside, backwards for the inside, and then we end up with KNO3. And now I say to you, this reaction produces a precipitate. If that is the case, what are the states of my products? PbI2 is solid because potassium nitrate must be aqueous, and if our reaction produces a precipitate, then that has to be it because it can't be the other one. Okay, so that is our precipitate. Do you remember how to abbreviate precipitate? That's a long word, so you can just write it as PPT. Okay, PPT, precipitate. PowerPoint, yes. So that is the formula equation. Okay. We're going to run out of time soon, aren't we? Let's just really, really quickly do the complete ionic equation. And when we do the complete ionic equation, we are going to take lead, Pb2+, and it is aqueous. So now we are doing our complete ionic equation. Next, we're going to take our NO3. How many NO3s do we have? We have 2 of them, yes. 2 NO3. What did I forget to do in my formula equation? I forgot to do something. I forgot to balance it. What would I need to do to balance my formula equation? 2 here and a 2 here. Yes? Now we're good. All right. So I have Pb2+, I have 2 NO3. How many Ks do I have? How many Ks do I have? 2. So you're going to write 2K plus. And how many I's? 2 I minus. And you're going to take a look at my reactants and tell me what you think of how I've written them. Why do half of them have states and half of them not have states? What should I put as the state for the K and the I? Aqueous. Excellent. Have I done anything else wrong? Yes. I do not have a charge on the nitrate ion, and it's not nitrate if it doesn't have a charge. It's nitrogen trioxide, and it is a different thing. Okay, so now our products. What do I do with my solid? I keep them together. Solids stay together. Okay, so we have our solid PB, I2, solid plus, and what do I do with my aqueous? Separate. So aqueous come apart, solids stay together. Aqueous apart. Ooh, they both start with A. And then solid. Ooh, look. Solid stays together. Oh. Gas probably won't come up, but gas stays together too. Okay? All right, and then we have our 2K plus and our 2NO3 minus. Don't forget the coefficient applies to both ions. So we have 2K plus and we have 2NO3 minus, and I need aqueous, and I need aqueous. That is our complete ionic equation. How do, yes? What about water? Water is just hanging out in the background. It's actually not part of the reaction. Acids and bases we'll talk about next day, okay? We're not gonna get there today because we got like 1 minute left, okay? Maybe only 30 seconds. So, to get the net ionic equation, oh, is it 44? We got 15 minutes left, oh my God, I'm so excited. Okay, so excited. So, we have, I'm still on last year's timetable, right? So, how do we go from the complete ionic equation to the net ionic equation? We cancel out, who are we going to cancel out? The things that don't change from one side to the other side. K plus is in the reactants, and so is K plus in the products. Who else does not change? NO3 does not change. It's floating around, and it's floating around. So we can cancel those out. Yes. So now our net ionic equation would be, what would be left in our net ionic equation? Pb2 plus 2I minus goes to Pb I2. What have I forgotten? States, aqueous, solid. Now, the reason that we're getting into this, even though really solubility is more like unit 3, the reason we're doing it now is that we're going to be measuring reaction rates. And when you look at a reaction, you need to be able to tell me, could I measure a change in concentration of the lead? Yes. Why? Because we start with lead ions. What do we finish with? Lead as part of a solid. So what will happen to the concentration of lead ions as time goes on? It's going to go down. Okay. Now, could I measure a change in concentration of nitrate? Does anything happen to the nitrate? No, it's floating around at the beginning of the reaction all by itself, and at the end of the reaction, it's still floating around all by itself. The volume hasn't changed, the number of particles hasn't changed. Could you use a change in concentration of nitrate to measure your reaction rate? No, because it doesn't change. You cannot use, what do we call those things that don't react? Spectator ions. Because it's with NO3, two of them. You can only tell from how it combines with the negative ion. If it was PbNO3,4, it would be lead 4 plus. So spectator ions do not react, and therefore you cannot use them to measure a rate because they will not change. And if you were not in my class last year, RXN is reaction. Okay? If you're ever finding that you can't keep up with the notes, don't worry. What have I done? I have done what with the lesson? I've recorded it. Plus, where would you find these notes? Class note, not class notebook, because class notebook does something weird that I don't like. I can't remember what it is, but I've tried it several years and I don't like it. So I just have a notebook, and then in Teams, let me just show you quickly in Teams where our class notes are, not the class notebook, which sadly I cannot get rid of because Microsoft does not give me the option. I said Teams, did I not? It's saying I don't like recording and doing other things at the same time, is what it's saying. Okay, do you see this here? Useless. Class notebook. There's nothing there, nothing. If you want to see these notes, where do you go? You go to class notes, and there you will find the link. And I'm just going to go through this really quick because sometimes you get there and you're like, it's ugly. I can't remember how to get out of this ugly screen, and I can't remember what to do with it. So we'll really quickly go through that, and then we'll do a single replacement. Actually, while this loads, why don't you guys try AgNO3 aqueous plus Mg solid. See if you can predict the products of that reaction. Ooh, it loaded. You don't have to do it just yet. Wait. Do you see this little bookshelf at the top left? That will take you to whatever you need. You're like, oh, I want data pages. Data pages. Click on it. Yes? And it's going to be really slow, but that should get you there. Does it have, I don't know. It's being extremely slow. So just be aware that you can get this screen from the little library and then you can close it again so it's not in front of everything. kind of reaction is this? This is a single replacement. How do we know it's a single replacement? We have a compound and an element. And last year we did a little bit of stuff like predicting if it would occur or not. We're just going to assume this reaction occurs because I've told you that it does. Okay, this one you do not need your solubility table for, and you don't need to really know much in the way of rules. What's going to happen in this single replacement reaction? Who's going to go where? This is a metal. If your element is a metal, who will it replace? It will replace the other metal. So I'm going to write my products and you're going to tell me how I do. Yes. I don't have enough NO3 minuses. Where? In the products. Well, I've only got one in the reactant, so I only need one in the products, right? No, why not? Mg is in column 2. Therefore, it has a charge of +2. It's an alkaline earth. Yes, charge is +2. Why is it +2? There's only 2 electrons in the valence shell, so it will lose those 2 electrons and become 2+. Excellent. Okay, 2 valence electrons. So it loses those 2 electrons when it becomes an ion. Over here, has it lost its 2 valence electrons yet? No. That's why any element in its elemental state by itself, its charge is 0, because it hasn't lost or gained electrons yet. But when it combines with nitrate, it will take on a +2 charge. And if that's the case, then what is the formula for magnesium nitrate? MgNO3, 2. All right. Anything else we don't like about the products? Yes? Silver should be elemental now, because where did the magnesium's electrons go? It had a 0 charge. It lost electrons, yes. Where did those electrons go? They went to the silver. Silver over here was Ag+. It's going to grab those electrons and become silver neutral. So whatever your element is, it should be neutral. Okay. How are we feeling about states? We need magnesium to be aqueous, and I filled that one in already. Could you have predicted that Ag is a solid? You know that metals are all solids unless like we've melted them, or if it's mercury. Okay, so metals in their elemental state at room temperature are all solid. Could you write a net ion? Oh, could you balance this first, please? 2 in front of AgNO3, 2 in front of Ag. Could you write a complete ionic equation, please? So remember, if you're doing the complete, if you're doing, yeah, you could go directly to the net ionic equation. And if you're able to do that and it just asks you for the net ionic equation, do not feel obliged to go through the route of complete ionic first and then net ionic. You can do that, okay? We'll focus on that a little more next day, okay? But for today, we're gonna go through the complete ionic. What would we have for a complete ionic equation? Ag plus aqueous plus NO3 minus aqueous. Huh? Oh, I need a 2. Yes, I need a 2. Good. 2 there and 2 there. All right, what else have I got? Plus Mg solid. There's our reactants. Often I find with complete ionic equation, I take 2 lines because it's so long. So what are our products? Mg, 2 plus, okay. Aqueous, plus aqueous, plus 2 Ag solid. And what if we wanted to write our net ionic equation? NO3, what are NO3? Spectator ions. I'll throw your homework up on Teams. Okay, so don't worry about getting it down now. It'll be up on Teams in just a moment or two. Whew. Okay. Hi. Yes.
Starting
Uh-huh.
here, on the test, do we have to write like all this part
Yes.
on the test?
Yes.
And on the exam as well?
Yes, although AP is kind of funny about what they give marks for, but I would do it just in case they are like, yes, I need that. Yeah.
And then I have another question. So, like, for example, for this one, then,
Yeah.
it's like, I would probably have to do this, right?
Yeah, but like when you're practicing, you don't need to do it every time.
Okay.
Do you know what I mean? Yeah.
And then also, I saw that on the answer key, you do this in like 3 different steps.
Oh, you don't have to.
You don't have to.
No, you can show it all in one place. Yeah, that's totally fine.
Because I was just like.
Yeah, no, it's totally fine.
And
You
then
can,
with this,
yeah.
do I also write this and then like since I'm like doing a unit conversion here.
That's fine.
So like.
That's okay.
How would I show this then?
You could say change in moles of zinc over change in time equals. I don't even know. You could do it. I have a feeling if that was on an AP exam, they wouldn't make you write the formula. You could just be like, okay, I'm gonna go do it.
Okay,
Yeah.
okay, sure,
Yeah.
thank you. On your test, we should probably do it, right?
On our test, it'll be like pretty obvious, right? Just because I want you in the habit of writing formulas because sometimes they get wound up about it and sometimes they don't.
Okay,
Yeah.
thank you.
You guys can close that little window if it's blinding you. Hello.
Hi, sorry, I have 2 questions.
Yes.
Would you mind explaining like why you do it at the highest point? Because it kind of went over my
Oh, the wavelength? Yes. Okay. So that is. Okay, so here. Let's say I want to measure something where the concentration, let's say that this graph is for concentration 1 molar. Okay. Now I want to do my calibration curve and I want to have 0.5 molar and 0.2 molar and 0.1 molar. Well, when I do 0.1 molar, it's going to be 1/10. So my absorbance is going to be not in a, like once you get too far to the bottom, it's like it's hard to read. It's not as accurate. Okay? You want a good strong absorbance. Okay? So if this is 1 molar, 0.1 molar, if I use this wavelength, whatever it is, 200, let's say, if I use this wavelength, I would have an absorbance of like 0.1, right? If I use this wavelength, I would have an absorbance that's greater, and so I would get a better result.
But don't you want like the lowest absorbance so the most light can shine through?
No.
You don't? So you don't want any light to shine through?
It's not that you don't want any light to shine through. What you want is you want to say, if I'm looking at green, let's say that this is a green solution, then that's red. It's going to absorb red the best because green is really good at absorbing red. Okay? And this wavelength will correspond to red. It does absorb all the other wavelengths as well, but it absorbs red the best.
Right, so you want it to, so you don't want it to pass through.
No,
Right, okay.
no. Because the thing is, it's a solution, so a lot of the light's going to pass through anyway. Like any, if you put food coloring in, you're like, oh, I can still see light through it, right? So you'll still get lots of light passing through. You can always dilute your solution if you need to. Yeah.
Okay, thank you. And then
Yeah.
the second question is, like, why does like absorption plus transmittance equal to like 1 or 100 or whatever?
No, because absorbance is the negative log of the transmittance.
Oh, right.
Yeah, so that's how they relate to one another.
Yeah. Sorry, I forgot that we learned that. But like, why is that?
Why does it do that? It's because that way when we do our calibration curve, instead of, if we did transmittance, we would have, where is it? 49. If we did transmittance, it would look like this. Yes, we would get a curve.
Okay.
Now, it's not easy to read numbers off a curve. It's not easy to get the equation of the curve. We straighten that line by taking the negative log.
Right.
Yeah?
Okay.
Yeah.
Okay. Thank you. What is AP Classroom?
What is AP Classroom? It is a source of problems and review material and et cetera, et cetera.
Okay, so I just sign up.
You just sign up for it, and at some point, maybe this weekend, I'll get a few things organized so you could, like, maybe say if you wanted to review some, I don't know, atom stuff over the weekend, you could be like, okay, I'm going to go take a look at my atom stuff over the weekend. Yeah. Yeah, it'll be more important as we go further and you're reviewing more. It's a really good source for review. Yeah. Hi.
I have a couple questions. So, I'm a bit rusty on chemistry.
Yeah, it's okay, no worries.
So, in the example here,
Yeah.
so lead goes from aqueous to solid.
Yes.
And then you said that the concentration decreases. I was wondering, how does that, because if it goes into a solid, aren't they more tightly packed together?
They are, but they're not dissolved anymore, and concentration is the concentration of dissolved ions.
Okay.
Yeah?
Okay, that
Yeah.
makes sense. And then
Yeah.
the other one is, in the reaction here, why, so, like, when we write it as the ionic one,
Yeah.
why are they all aqueous, or which ones
If
are
you've
not?
got a double replacement, they'll both be aqueous to start with, otherwise it doesn't work. If you've got a single replacement, you'll usually have like a metal, which will be solid, and then an aqueous solution.
Okay, so in double replacements, they're all going to be
Aqueous, and then your products will be whatever they are produced.
Okay, and then, but in a single replacement, the metal that's
The metal's
by
going to be a
itself at
solid.
the beginning is going to be a solid.
And the metal
then
by itself at the end is going to be a solid.
Okay,
Yes.
that makes sense.
Yeah.
So we were doing a single replacement. I don't know, but yeah, okay, that makes sense.
Cool.
So for this one, at the beginning, would this be Mg2 plus still?
No,
No,
it would
it would
just
just
be
be
MG
MG
solid.
solid. Okay,
Yes.
that's what I was
yes,
wondering.
correct,
Okay.
correct, correct. Yes.
Okay, that's
Yeah.
all I had. Thank you so
Cool.
much.
No problem. Hello.
I just have a question.
Yeah.
Earlier in the double displacement,
Yes.
you said that if the question say it forms a precipitate, so we wrote the solid.
Yeah.
But if it doesn't say, then do we know what
If it doesn't say, it will, the thing is on the AP exam, it will say.
Oh, okay.
On the regular one, when we do this in Unit 3 and it's like officially part of the unit that's being tested, which it's not really right now, we will use this table. And you might discover that if I had, let's say, sodium nitrate and I reacted it with potassium chloride, I would end up with no precipitate because everything would be soluble.
So it's always soluble.
So if things are always soluble, there would be no precipitate if your products contain things like that.
Okay.
You can also end up with two precipitates.
Yeah.
Yeah, and in fact, I'm wondering if I have my solution. And you're welcome to take this with you. Okay. But this is sort of showing you like what's going on. So we start with the dissolved NaCl, the dissolved AgNO3. We discover that if we look on our chart here, our product AgCl, Cl plus Ag is low solubility. So that will be our solid.
Okay.
And then Na is soluble with everything, so is NO3, so they will keep floating around.
Yeah.
And so that's how we know that we have our solid here and these two are aqueous. Okay?
But if we have like both products compounds super soluble,
So,
then we choose one.
two precipitates. Okay, so we have copper sulfate, which is soluble, strontium hydroxide, which is soluble. Now, when copper gets in contact with hydroxide, we look here and we say hydroxide, copper isn't here, so it would be here. So that would be low solubility, so it's a solid. So you go, okay, I got a solid. That one's a solid. Then you say, what happens when I put strontium with sulfate? Let's look up sulfate. Strontium sulfate is low solubility. And so, oh, I got another precipitate. And we're just going to assume we have the right proportions here and we don't have any excess reactant or anything like that. So you would end up with a solid and nothing else. Okay? And then you can also have, if both your products are soluble, you get no reaction because everything was floating around and now it's just been mixed.
Does it ever insist that this one will form like one precipitate?
No. Would you like this?
Yes.
Okay, here, I'm going to give you the whole thing.
Yeah.
That way, at least it's got things on the front. If you don't use any of it, it's fine. But yeah, they did this last year. And you may or may not have done some of it.
I already have.
Do you have this one?
Yeah,
okay,
this one
so this is just this 8.3 here.
Okay.
So you can take a look at that and let me know if you have questions and stuff.
Yeah. And I have a second question.
Yeah.
It was about the calibrate curve.
Yes.
Like, why did you say that it's gonna not go straight after?
It just does that.
Oh.
That's how Beer's law behaves. Like absorbance doesn't go as a completely straight line with concentration. It does for short distances, it's straight, but then it'll start curving.
Like the trend is not always.
It's not a perfect line because life is just not perfect.
But doesn't it say absorbance is like increased linearly? So it's supposed to.
Yeah, but it only for short distances, and then it's like, oh, whoa.
Yeah. Okay. I got it.
Real life, sucks. It's not perfect. Yeah.
And the last question is that do you know if the spectrophotometer unit is on the BLB textbook?
Spectrophotometry, maybe not.
Yeah.
Maybe not.
Okay.
Yeah. It's more of like a lab kind of thing.
Yeah.
And I got to get your homework up here, but yeah, on the homework it's going to be like, go use the spectrophotometer. We're going to go over a bit more of it tomorrow. Okay? Yeah.
Thank you.
Okay, cool. Hi.
I was wondering if there's a space in AP Chem because I wanna join the class and like yeah.
Okay, you know that there's like all the stuff that they did last year that you don't know, right?
I'm not planning to take the AP exam.
Okay.
But I just wanna.
You want to be in the environment.
Yeah.
Come on. I love
Is
it.
there a space? Oh, I see. Okay. I'll email my counselor right now.
Okay. Who's your counselor? Ms. Aaron. Okay, I will also have to email her. Yeah, because she'll probably want permission because they get a little wound up, because we get a little wound up about who can come in. And I wouldn't say that to just anyone, but your chemistry skills very strong. So yeah.
Thank you.
Did we do solutions last year?
I remember doing dilutions.
We did dilutions. You know what I'm going to do though? I'm going to give this to you. Okay. Yeah. So, and should I just give you everything else too?
I'll come back.
You'll come back. Okay, good. Okay. Sounds good. Thank you, Dan.